Okay. Rich text generation is something that is not, that's not alien to anyone now, right? Essentially, if you want to write an essay on Indian Independence Day, all you need to do is to just go to beta.openai and essentially just start, just ask a very simple prompt, write an essay on Independence Day, and you get a very good generation, right? Or on the other hand, if you have other kinds of tasks, like for example, generate 10 MCQ questions, let's say with options on deep learning, it basically nicely generates those kinds of things, those kinds of outputs, MCQ questions with options. You can actually put them up in your exam for students and so on. Besides text, actually a lot is happening in this space, which has to do also do with multilingual text. For example, explain in a sentence in Telugu what is backpropagation neural networks. So thanks to these large language models, now we can actually generate multilingual text or write a fairy tale about a troll saving a princess from a dangerous dragon. Lots of tasks are possible. Multilinguality is possible. And not just that, similar models are also used to generate code in GitHub Copilot. Similar models are actually now also used when augmented with image-based decoding or image-based representation generation. You can actually do all kinds of interesting things. For example, along with a text caption, a photograph of a bust of Homer, and just provide a small image prompt, you can actually generate a bust of Homer across different orientations. So no artist needs to do this now. Across different orientations, different lighting conditions, and so on, you can automatically generate these. Word to paper basically said you could do vector arithmetic, like king minus man plus woman is approximately queen. Now you could actually do the same thing with a combination of text and images, right? So you could basically say convert a Victorian house to a modern building, and this is what you get. Or translate a Tesla car to an old style car. This is what you get, right? And of course, you can actually do image inpainting, which is basically about taking a part of the image and then saying in text what do you want, be looking for food on a leaf, and then here you go, right? Of course, it has several implications across sectors like the movie industry, interior industry, and so on, right? So all of these interesting things that I showed you in a minute or two basically are pumped thanks to large language models. In this talk, I'm not going to talk about more use cases, but I'm going to talk more about how these large language models work, what is the history, how it has evolved in the past 5 years or so. Therefore, this is the agenda. I mean, the agenda is to, in fact, go over several different kinds of models and sort of talk about how they work in general. Right? And towards the end, I'll basically wrap up with GPT-3, InstructGPT prompting kind of stuff, which folks in the later talks in the series will take over from. Okay. So it all started with the transformers coming up, right? So let's therefore talk about that first. So before 2017, NLP was very different. It was mostly natural language understanding and not so much of generation. It was mostly English and not so much of multilingual. Multimodality was not even there. Even if it was there, it was in its infancy, not as accurate as it is now. Most models were rule-based, traditional machine learning-based. People would believe in statistical machine translation rather than deep learning-based translation. Even when deep learning started coming up, people started using things like RNNs, LSTMs, GRUs, bidirectional LSTMs, stacked LSTMs, encoder-decoder LSTMs. And that is when people realized that, hey, deep learning has a promise to be better than traditional machine learning or rule-based methods. And then attentional LSTMs. And then attention led to attention is all you need, which is basically the transformers work. Transformers basically said that, hey, while you provide a sentence as input or some English text as input, or for that matter, multilingual text as input, you can probably learn a better representation for every word by transforming its representation several times by paying attention to other words in the input. And it was a natural sort of a transition from encoder-decoder LSTM-based models to encoder-decoder no recurrent connections-based models or completely self-attention-based models. Self-attention, basically the main purpose was to sort of learn relationships between a pair of words. And then people said, why just one relationship? Let's learn more. And that lead to multi-head attention. Right? I mean, and I will not go over the formulae, but most of us sort of can relate with these things. Essentially, in transformers, for every representation, you get three transforms, three representations, QKV, query, key, and values. And then you try to sort of look up or come up with a transform representation at every position, much like you would do with a value depending on a key value store, right? So that's that. It's just that the values and the key value store are all in the same sequence. So that's that. And this is a very nice animation to sort of show how transformers work in an encoder-decoder setup. A lot of information is passed across all words. They learn from each other, their own revised representations until until it is time to actually start decoding. And when it is time to start decoding, they sort of take information from the last layer of the encoder, and the decoding happens word by word. So one word at a time. Decoders only pay attention to the words generated on the decoding side so far, and encoder, essentially last layer of encoder, helps the decoder to decode those words one by one. Yeah. Transformers was great, but it was not still transfer learning. So people had to learn transformer models from scratch, and that is when people started thinking about about pre-training as a concept in NLP. Vision folks had progressed a lot. They had basically come up with pre-trained models like ResNet, DenseNet, LXNet, and VGGNet, and so on. And this is when, I think the NLP folks said, we will also do some sort of pre-training and transfer learning. So the concept of pre-training came in, pre-training and then fine-tuning. People basically said, yes, let's have a multi-layered bidirectional transformer encoder and call it BERT. So the idea was vision folks said, hey, pre-trained models are models which understand how to obtain features from images. NLP folks said, oh, BERT will be a model which will understand basic English. It will be like a kid, like a fifth grade kid who understands basic English. But then yes, if you want to make it learn sentiment analysis, you can fine tune it to do so. Right? So that is what people did in BERT. They made the model learn English using MLM and NSP. Mass language modeling, much like you would really make a kid learn, right? Hide some tokens in a normal English sentence and make the kid guess those guess those missing words. Or next sentence prediction. Yeah, I mean, given two sentences, hey kid, do you think that the second sentence follows from the first one? So that was a very obvious way of making a model learn English. Once you had a pre-trained model which learned from a lot of English, around 800 million books words and 2.5 billion English Wikipedia words, you could fine-tune it for various purposes. Right? In fact, the model was trained such that it could take two sentences as input, which was very suitable for several kinds of tasks like query document matching or query add matching, or given two sentences, find if they're paraphrase of each other or not, and so on. So on the other hand, for natural language generation, people came up with GPT. The same OpenAI came up with GPT 2018. They said that, hey, we'll only care for the decoder part of transformer, and hey, that will be our GPT model. Again, you could basically pre-train it on auto-regressive modeling, in the sense next word prediction in simple words, with 7,000 books. And then they said that, hey, our model is still not very generic, so we will still fine tune it. So they still had a fine tune phase. They basically said, okay, for classification tasks, we will still fine tune it, just like BERT guys said, hey, we'll fine tune it for various kinds of tasks. Right? So for classification, you'll fine tune it, entailment, similarity, multiple choice questions, all of them. They also had their own recipes of enabling fine tuning in that senses. Now, these streams basically, so transformers was the super parent. BERT and GPT sort of became like the forefathers of anything in NLU and NLG. And then people started experimenting with hundreds of variants of BERT, some of which became super popular, like RoBERTa. Right? RoBERTa essentially was robust BERT. They made it robust in every aspect, increasing the pre-training data from 16 GB to 160 GB, training way longer, large batches, large vocabulary. Also, they made out, they basically removed a problem that BERT had. NSP, actually, people found next sentence prediction did not really help BERT much. So they said, let's ditch it. So, and that's how RoBERTa came up. Again, of course, showing much better results across several tasks. Then people realized that, hey, whether you train a BERT or RoBERTa, you're not doing very efficient training, because you're only learning from those tokens which were hidden. So you're making the kid learn English, but only by hiding a few words. And then it only learns 15% tokens. In fact, you say 85% words, but 85% extra words to make the kid learn just 15%. And that is when people came up with ELECTRA. They said it is much more efficient because, in fact, it has two parts to it. One, which looks like BERT, and the other, which is more of a generator, again, which looks like BERT in that senses, but does MLM. So you train this generator kind of a guy in an MLM fashion. So mask some words, mask language modeling fashion. So you mask some words and ask the generator model to generate generate words, guess the word. So for example, for this guy guessed the. But for cooked, it basically, guessed 8. Now that's interesting, but it guessed the masked word anyway. Yeah. And then for the discriminator part, well, you train it just like the architecture is still BERT, but then you do not train it for mask language modeling. You train it for replace token detection in the sense that this discriminator tries to just figure out whether the token is original or was it replaced when it was passed through the generator. Can you please mute yourselves if you're not speaking? Thank you. And folks found that the generator, you could actually have a very small generator like a 3-layer model, and still it would really lead to a very awesome discriminator. Thus, the effort in coming up with a separate generator was sort of justified. Of course, after training is done, you could delete the generator and just keep the discriminator. Several graphs showed that yes, the training was could be done in much smaller amount of time, much smaller amount of compute power, while giving better results. Right? So people call it RTD, replace token detection compared to MLM in BERT. And then it was our own team, at MSR, which basically created DeBERTa, one of the best models right now on the glue benchmark or super glue benchmark, right? Where people said that, hey, while passing on inputs to BERT model, you are actually mixing content and position together. So the token embeddings and the position embeddings are mixed together. Can we sort of disentangle them? Maybe it is not good to just add the two and mix the signal together. So that is when people said that, hey, rather than having just QKV, a query key value and so on, right? Let's basically have these separately for content and separately for positions. So they had QC, KC, VC for content, but QR and KR for positions. VR was not really required because there was not much of a point in computing a revised representation of a position depending on the position, right? So that's why basically the content and position embeddings were disentangled. That is why decoding enhanced BERT with disentangled attention, right? And then they actually computed attention more or less in the similar manner as you would compute in a typical transformer, QK transpose in that senses, but with slight changes because now Q has gotten divided into 2 parts, K has gotten divided into 2 parts, and so on. They also said that, hey, while computing these position embeddings, we'll use relative position embeddings so as to make it more accurate. But then absolute position embeddings are also super important. So how can we make use of that? So as an additional context in the last layer, so transformer has so many layers. In the last layer, they basically said we'll have a special block, which will not just take, which will basically use the absolute position embedding as a special input only for the last layer, and use it to define the the query value for the last transformer layer. Right. So essentially saying after BERT, several improvements happened. RoBERTa, ELECTRA, DeBERTa, and DeBERTa is actually one of the most awesome models right now for NLU. Right. Now, in the NLG space, GPT was good, but it was decoder only. And people soon started feeling that, yes, you need an encoder-decoder model rather than a decoder-only model for more accurate decoding or for more accurate natural language generation. And then people came up with these two popular models, BART and T5. And very recently, MSR came up with DeltaLM, right? Which is basically TOLGV2. Right? So BART basically said, hey, it's an encoder-decoder model. So I have to basically bring in the combination of the encoder and decoder. So the encoder was trained using MLM. The decoder must be autoregressive in nature. So you combine the MLM and the autoregressive ideologies in the same model. But while doing so, in fact, you make it more robust. So the idea was essentially, hey, this particular part, the encoder, the input that goes in, we can actually add noise to the input, not just in terms of masking some tokens, but other kinds of noise also. So MLM just said mask the tokens. Hey, but we can do many other things. For example, we can mask several tokens and basically meaning mask phrases together, spans. We can permute the sentences. The output is the same. You, of course, expect the denoised output. But then input, you can add various kinds of noises. You can delete some tokens, you can mask some tokens, you can permute tokens, you can rotate the document, and so on. Right? And then once you have the model ready, well, you can actually, or rather, the model is pre-trained using these kinds of things. You can actually fine-tune it for various tasks: sequence classification, token classification, sequence generation tasks, and so on. And then came up the popular T5 model from Google, which was also an encoder-decoder model, a pre-trained model, but trained on very large amounts of labeled data, very large amounts of pre-training data, some 750 GB data. More than the model, in fact, the data became more popular because that was the main reason why the model is so accurate. And it also was the first time that people started talking about this concept of prompt. They basically brought in this concept saying, hey, my model is a very generic model. I will actually give it a prompt, translate English to German. And this was not new. This is way back in 2019. They said, hey, we'll bring in a prompt. And then whether it is a classification task, generation task, whatever task, right, I'll basically make it a text to text task, right? Even if it is about sentiment analysis, which essentially means that I want to take a review as input and essentially come up with some score, I'll still model it as a text-to-text task, right? And then they tried several other, hyperparameters so as to improve on the hyperparameter set in BERT. But then the main contribution there was to basically be able to say, using different prompts, you can actually learn a single encoder-decoder model which can perform several tasks together, right? And of course, much more accurate. All these advancements, of course, led to multilinguality. So people said, hey, why can we not do multilingual models now that we have transformers which are very robust at doing English? So people took cues from BERT and came up with XLM, which meant that you could take MLM and NSP. NSP could be thrown away because people realized next sentence prediction didn't work. A T5 model realized that, several other people realized that, RoBERTa realized that, and so on. So people ignored next sentence prediction. They focused more on MLM. And then also causal language modeling. Causal language modeling is the same as autoregressive modeling. So they just borrowed that from GPT folks. And then they also said, hey, since it's multilingual, it should learn multilinguality from translation data. So they said that, hey, causal language modeling, I can borrow from GPT. MLM, I can borrow from BERT, but then it has to be multilingual. So let's basically therefore use parallel MT data, parallel machine translation data. Let's say English and German subtitles from open subtitles dataset and so on. And therefore also learn this translation language modeling, which was basically saying that, hey, I have some part of English input and also French input together next to each other. And then I mask a few English tokens. And the hope is that I'll be able to guess the word curtains using its French representation as well, which is hopefully not masked, while also depending on the other words in the input in the English side itself. Right. So therefore, these embeddings actually learned not just how to guess a word from the other English words in the input, but also how to guess a word based on the other non-masked French words in the input. Right. And then there were folks who basically took translation data to the extreme. They extended this XLM model, which we just talked about, to Unicoder. Again, our own folks from MSR, right? Basically saying that, yes, MLM, TLM is good. And I can actually do some interesting ways in which I could use translation data. So they called it, they basically called it this one as recovery. Yeah, so cross-lingual word recovery. So here, the idea is, this is the same as TLM in some ways. You basically put English and put Chinese, and then here you're trying to, so you put English, you put Chinese here, the lower one, English, Chinese, and so on. And then you try to guess English word based on other words, for example, Chinese words and so on. They also added two other tasks. One task which basically said that, hey, if I have an English sentence and a Chinese sentence, are they basically, translations of each other or not, positive or negative thing? And then they added yet another task which basically said that, hey, if I have English token embeddings and parallel sentence in Chinese, and let's say if I compute similarities between them in their embedding space only. So this is basically similarities in the embedding space. It is basically like saying I'm reading an English sentence by attending on the appropriate Chinese words. Okay, reading an English sentence being influenced by Chinese words. And those Chinese weighted English embeddings that I get here, I pass to the transformer and it should be able to get or recover my English words appropriately. Okay, recover my English words appropriately. So basically saying they just made better use of the translation data and came up with better results. Okay. Now, not just that, people proposed NLU kind of models for multilinguality. People also came up with multilingual versions of NLG models like BART. So now in this particular case, you would actually make use of cross-lingual data. So rather than just using English sentence only, you would train BART in a multilingual manner. Take English inputs and generate English outputs, but also take Chinese inputs, generate Chinese outputs, and so on. So that led to multilingual BART, where they basically started off with 25 languages and then later extended to 50 languages overall. And then came MT5, which is a revised version of T5. They basically also came up with a MC4 data set, which is a revised version of their C4 data set, the colossal data set that we talked about. They just made it multilingual. In fact, this data set is actually a standard used across several other pieces of work. This data set is publicly available. People on Hugging Face, several people take subsets of it and make use of it. So that was multilinguality until very recently. I mean, so T5 became popular and was quite popular for quite some time, more than a year, until recently when our own MSR folks came up with DeltaLM, which is TOLGV2, right? Where people said that, hey, we need to have a multilingual encoder decoder. And therefore, we will essentially initialize both of them using InfoXLM, which is another MSR work, right? InfoXLM is a multilingual encoder model. So we'll initialize both encoder and decoder using that. And then we'll actually change the decoder setup a little. So rather than having these three sublayers in the decoder layer of a decoder layer, you would rather have four sublayers. Self-attention, feed forward, cross-attention, feed forward. The reason for doing this is that they wanted to ensure that none of the weights in this model are trained from scratch. So this kind of a setup basically helped them initialize even the decoder layers using an InfoXLM encoder. So the idea was typically people so far have mBART, MT5, they typically train from scratch, right? And therefore they could reach to a particular level of accuracy. But DeltaLM folks said, no, we'll actually reuse the learning, pre-trained learning from InfoXLM, and we will further train on it, no longer training from scratch. And that was possible only if you change the decoder configuration a little. So therefore, if you're basically optimizing, let's say TOLGV2, you will actually get into a little bit of pain because it doesn't really follow the same optimizations as standard transformer in the decoder side. And then they also basically added two interesting loss functions, span corruption task and translation span corruption task, which was basically masked language modeling and translation language modeling, practically. Mask words either in just one language or masked words when you are talking about two things across, or other two languages as input, and mask words in one language and guess those words using other words in the other language. Thanks to these advancements in NLP, the vision guys actually liked for the first time. I mean, or rather, very few times it happens that vision guys actually like what is going on in NLP, right? And then vision guys said, "Hey, Transformer seems to be doing really well in NLP. Let's basically latch on to it for even vision tasks." That is the first time that people actually started looking at images and converting them into format that can be fed to a transformer. So vision guys basically took their own faster RCNN models, tried to figure out objects, convert them to features, and then pass them as extra inputs alongside text as part of the transform model. Now, clearly, if you're feeding in text tokens and image tokens together, you need to come up with some other objective loss functions in pre-training loss functions. So rather than just depending on masked language modeling, now it is masked language modeling with image. So basically, as I'm trying to guess a particular word here, let's say if I mask this particular word in English, I want to guess that word here. But now I don't need to just guess based on these other words, but I could actually also make use of these object tokens, right? So essentially some images, so as to basically guess that, yes, this word is racket, right? In some ways, at this level, you could think of images as just another language. And if you think about TLM, translation language modeling, you could literally think about images as yet another language, which is whose tokens are actually used to guess the masked word in English, right? Thanks to attention, people could actually come up with these kinds of interpretations that, hey, if I am answering a question based on this image, or if I am just coming up with a caption based on this image, I could actually come up with these attention masks, which can explain and interpret, hey, why this caption makes sense in the context of this image, and so on. Right. That's that. And then people extended these kinds of multimodal models. VisualBERT was probably one of the first multimodal models which could do interesting tasks like visual question answering questions in the context of an image, or visual common sense reasoning, and so on. So multiple such multimodal tasks. And that is when, in fact, in the past 2 or 3 years, multimodality has actually gained a lot of momentum. People extended this model by saying that, hey, rather than just combining multimodality in terms of masking, I can actually use multimodality to influence the way transformers work themselves. So I could use vision embeddings as queries and text embeddings as the keys and values. Or on the other hand, I could use text embedding as queries and vision embeddings for keys and values, and come up with a more, with a more code transformer layers, with a more, with a better aligned or with a better principled combination of text and vision tokens in the input, right? And then they also said that, hey, we could also come up with more interesting pre-training loss functions. So the idea is now you want a model which is pre-trained to understand text and image together. So computer vision folks had trained models which could understand interesting features out of images nicely. Language guys had understood how to basically make a model learn English, or for that matter, across languages, 100 plus languages. Now, can you do the two together? Can a pre-trained model reason about text and image input together like a kid would do, like a 5-year-old, like a 5th grade kid would do, right? So, so one of the ways, of course, in vilBERT, in VisualBERT, it was like, hey, you take the image, you take the text, and you combine together, and you get you basically try to fill in the masked words. But then these guys said, hey, can I actually also mask image tokens, right? So, and then the idea is that, hey, of course, if I mask text tokens, I want to predict that mask token. But if I mask an image token, I want to at least be able to predict what was the class to which that particular object belonged to. Was it a table? Was it a laptop? Was it a bird flying, and so on? Okay. And then they also came up with other kind of loss function which says, hey, if I have an image, I have some text tokens. Do these text tokens apply to the image which exists as the other input, right? Is it aligned or not? Right. Based on these kinds of understandings, people came up with really awesome models. Until very recently, just last year, people came up with this model called CLIP. And again, OpenAI came up with this model called CLIP, which just is a super awesome multimodal model. Now, most of the multimodal world actually uses CLIP. So they came up with a very simple idea. The idea is that, yes, there is a text which is processed using text encoder. There's an image processed using some image encoder. Now, text and image encoder could be anything. Text encoder could be a transformer. Image encoder could be, ResNet, VGGNet, DenseNet, whatever. Yeah. And I come up with some representations. So the idea is that if in a batch there were like 100 aligned image text pairs, then image and text, and then all I want to say that yes, this image is a caption. This text is a caption for this image. So overall, I have 100 square combinations possible, but only 100 of them are valid. All CLIP wanted to do was to really apply a contrastive loss. So all that it does is to take the image embedding and the text embedding and ensures that those 100 which are aligned should have much more similarity compared to the remaining 10,000 minus 100 which are not aligned. That is a very, very simple principle based on which CLIP is trained. It trains this text encoder and image encoder. And then once the training is done, of course, you can use the two nicely for multimodal effects. Right. Now, while all this was going on, we at Microsoft were also thinking how to deploy these models. And while thinking so, of course, we couldn't deploy them on our web servers because, yes, I mean, it takes a whole bunch of GPU power, and our GPUs don't have that kind. Our web servers don't have those kind of GPUs. A cost per user would go up if we were to actually include GPUs in large amounts of quantities of them on our web servers. So we wanted to ship these within limited capacity, limited latency. And therefore, people came up with these ideas of compressing models, right? Distilling models. Yes, language models are large now, but then you can't ship large language models. And then people came up with things like distillation. So the idea was rather than using the same labeled data to train a very large and a tall model, a teacher model, can you train a small model, like a 1-layer, 3-layer model, which can be shipped clearly, right? Because a small model takes less compute power, takes less latency, and so on. But then people were like, hey, is there any benefit of doing so? I mean, if you have limited amount of labeled data, you could train the large model, you could train the small model. So big deal. I mean, you can't ship the large model, so therefore train the small model and ship it. But then people found that, hey, there is some wit, some intelligence in actually taking the teacher model and somehow influencing the student to learn from the teacher as well, besides just learning from the labeled data. But what is the extra learning that the teacher provides is the question. So to answer that, look at this image. Now, if I were to ask a human to label this image, they would most likely just say it is a dog. But if I were to ask the teacher model to label this image, the teacher model would say, hey, it is 30% dog, 20% Trump, 5% cow and 0.5% bush. I mean, if these were the only categories, clearly, there could be more categories and so on, right? The idea is that a teacher model understands soft labels. It understands that, yes, dog and cow can look somewhat similar, right? Or a cat and a lion can look somewhat similar. No human would call cat as a lion, but a teacher model would understand these cross-class correlations, which are significantly important and much, much richer as a data for the student to train on, right? And that is why people came up with this method called distillation, or a student-teacher network, and clearly found it to be much more accurate compared to training just a small model from scratch from the label data. Right? Now, this simple ideology could be thought through from several perspectives. Like, people could try to understand what loss function to use. So how do you ensure that this logits or the soft output from the teacher is used as a nice knowledge for the student? How do you make use of that, right? So you could basically ask the student not just to guess the top label correctly, but also guess the distribution across labels as nicely as the teacher, right? And that's basically that can be done using different loss functions between distributions, like squared loss, KL divergence loss, JSD loss, and so on and so forth. In fact, what people found a nice benefit out of these student-teacher networks is that you could also use large unlabeled data. So if your labeled data was 5 million, you could basically use that data to train your student model by making sure that the student conforms to the hard labels that humans had provided, and also the soft labels the teacher is provided on those 5 million. But after that training is done, it's not done. The teacher could actually take the remaining unlabeled 500 million examples and come up with soft labels. And this time the student surely does not have a human label to learn from, but has a lot of this knowledge from the teacher to learn from. 500 million seemingly unlabeled data, which was labeled by the teacher. Right? So it turns out that this kind of second stage of further fine tuning the student just from unlabeled data with labels from the teacher leads to significant gains across several deployments inside Bing. And then people came up with several other formats of doing the student-teacher learning. That, like for example, why just depend on the last layer logits? Why not have the third layer from the student learn from the 12th layer in the teacher, and so on? Like, why not have multiple teachers? Like, we have an English teacher, math teacher, science teacher, and so on in school. Why not have multiple teachers? In some settings, it was actually very obvious to have multiple teachers, like machine translation. So there could be an English German teacher and a French Spanish teacher, and French to Spanish translation teacher, and so on. And then your student could be learning from each of those teachers nicely, right? So that was about compression, and distillation is the most popular compression technique that we all use so as to have transformer-based models, these large language models deployed in the short way. Right? But then another problem was how to leverage large data, right? So query document matching, yes, you can do just based on queries and snippets. But then, hey, what if I wanted to use the entire document body? Can I still do query document matching? Transformers basically are not very good at handling large data or large inputs. And that happens because you are transforming every position, every token based on every other token, which basically means that in transformers, there is full n square attention. Every token is paying attention to every other token. Meaning, if you had like 500 sized input, 500 token input, you would require 500 square, order of 500 square time complexity to run that model. Clearly, this meant that you cannot scale it to like 1,000 or 10, you cannot scale it to like tens of thousands of input tokens, like might be required when you have lots of context or when you have long documents to process, for example, in summarization task or query document matching, where you want to pass the entire document as input. And that gave rise to a whole bunch of work, which basically tried to reduce this complexity by bringing in linearity. So they basically said that, hey, not every position needs to look at every other position. Let it look at only the nearby position. So if I'm like the 15th word in a 100-sized input, well, let me look at only 10th word to 20th word wala window, right? So only look at a window of 10 to 50, 10 to 20, right? Or a little dilated window, meaning I'll look at maybe 5th word to 25th word, but after hopping by two, right? Or essentially also global plus side sliding, in the sense that, yes, I'll look at these 10th word to 20th word ka window. I'll not look at everything, not at everything, but only a small sized window. But I'll also care about some special tokens like the CLS token or some other any special tokens that might be there, which carry a lot of information. And therefore, I should always pay attention to those special tokens in that sense. Right? So this is basically longformer, but well, there came up several other models like linformer, reformer, and so on, which are very meaningful when we care about full body vectorization and projects around that. Right? Now, if you are training models, especially for multilingual use cases, like say translation, you can easily have multiple models, like English French model, German to English model, Chinese to English model, and so on. But if you have so many models, then for 100 languages you will end up with 100 C2 models, or you basically train one single model, and then the problem is accuracy. You lose accuracy, right? Essentially, it's not going to be as good as like 100 C2 models individually, right? So what is a good way? I mean, how to handle this is, on one hand, you have high accuracy, but like 100 C2 models to maintain and store. On the other hand, you have like one model, but then a little lower accuracy. And that is when people came up with this concept of adapters. They basically said that, hey, I will have one core base model in the sense that I'll have only one encoder decoder model. However, for specific language pairs, I will learn these small little layers as part, as part of the, or rather just after the feed forward sublayer in every transformer layer. I'll add these little adapter layers. So what are these adapter layers? They're actually just a one single hidden layer network. So which essentially just does a down projection, has a bottleneck layer, and then an up projection. So these adapter layers are actually there in every transformer layer just after the feed forward, and they essentially make sure that, or other, and these little small adapter layers are the ones that are actually trained for each of those language pairs. It's like saying, hey, I have a general purpose model, and then I learn very small little adapters to adapt it to different language pairs, right? So, and that basically meant that all you needed to keep is 100 C2 adapters, but one big large model. And then people observed that, yes, these adapter-based models were as good as actually these 100 C2 models trained separately. Low space, good accuracy, right? People use these adapter models for various purposes. In fact, Orca actually, I think, popularized the use of adapters significantly in the past 1.5 years. And then there was craze for actually adding a whole bunch of parameters in the model. So how can you sort of keep adding more and more parameters? Can you make trillion-sized models, and beyond, right? Now, a single machine surely can't handle trillion-sized models, even with all kinds of parameter sharding and so on, right? Where you can actually put different parts of the models in different machines, RAMs of different machines, right? There were needed a clever way of doing this, where you can actually increase the number of parameters in a model. And yes, you will of course store those parameters across machines, but then also get very good accuracy, right, with efficiency. So in the hope of leading to trillion-sized models, people came up with this thing called as mixture of experts. The idea is again very simple. So on the left side, what you see is the standard transformer and transformer layer. There's a multi-head attention, there's a feed-forward attention, and so on. And then what this MOE or mixture of experts does is to basically replace your feed-forward sublayer by every alternate feed-forward sublayer by multiple feed-forward sublayers. So in parallel. So what you have is this one is a standard one. So every alternate transformer encoder actually has a standard feed-forward layer, but then the other alternate transformer layer actually has several feed-forward experts. So they're called as experts. Now you have several experts, and they are all in parallel. They all operate in parallel. So when you get a training instance and the activations from the multi-head attention layer, well, you can actually potentially pass it to, let's say, 128 different experts, right? The more the merrier. The more the merrier for the accuracy. The more they are, it also means more compute power, more number of weights which are being trained here, right? And to do so, what people said is that you can actually train them in a distributed manner. So you can have like 128 different machines, and on each of these machines, this expert lies. So the first machine contains everything else is the same. Just for these experts, the first machine will have only FFN1 expert. Right? The second machine will have everything else, and then it'll have FF2 expert, and so on. Right? Now, of course, training also had to be like a little, efficient and inference as well. So therefore, they said that hey, whenever an instance comes in, it's not like I'm going to pass that instance to all of those 128 experts and make them train and learn and update their weights and so on, because that would be very inefficient. So at train time, maybe you can take that inefficiency. You surely can't take that at test time. And therefore, what they did was to essentially pass that instance that comes in to max of 2 experts, right? So they decided to have 2 experts. In fact, later in a paper called as switch transformers, which popularly got to be called as switch transformers, they said, hey, we will train, of course, 120 experts, but we'll switch to one of those 128. We'll not basically pass it even to 2 experts. Okay. Now, which two is then the question? Hey, which two should you pass at train time or the test time? And then people came up, there's a nice formulation how people decided which 2 experts to choose out of 128, clearly depending on the current input, and also ensuring load balancing. If you have 128 experts, 128 machines are being used, you want to ensure that, hey, all of them are being used in a fair manner with load balancing and so on. So that was the story, folks. I mean, I think people started small by understanding that attention is all you need. Then people went on to doing natural language understanding using BERT, RoBERTa, ELECTRA, DeBERTa, and so on. And then said, oh, now we are at a stage where we can do awesome generation. So yes, let's do BART T5. Expand to multilingual things. Start with 25, then to 50 languages, and then to 100, right? 100 plus languages now. Almost every multilingual model supports 100 plus languages. Then to multimodal modeling, why not bring in images as well? And then audio, speech as well, right? Though I didn't talk about it. Then thinking about how can we deploy these models? How can we deploy them in distributed setups and so on? Most recently, people have started thinking about how to build a general model, right? The idea about machine learning is that so far traditional machine learning and all machine learning so far has been task specific, task based, right? I want to do this task, I get a labeled data for that task, right? And I train that model. But humans don't do it this way. I mean, humans do not require large supervised data sets to learn language tasks, right? There's a person, you basically just tell them that, hey, this is the task, this is how the task is done using 2 or 3 examples. The person just learns that how to do the task really quickly, right? So what is enough for most humans to take instructions is a brief directive in natural language. Please tell me if this sentence describes something happy or something sad. That is all you need to tell them, right? Tell people, right? And also maybe sometimes some demonstrations to tell them, hey, this is how it is done, right? This is how it is done. So for example, if I have to teach my kid, hey, how to basically, stack books together, maybe I'll tell her, hey, this is how you stack 1, this is how you stack 2. And then I tell her, hey, come on, now keep stacking books. And she does it so well, right? So, and this is the exact philosophy behind GPT-3. So people said that, hey, there must be a way of mimicking this way of human learning where we have a central core. We sort of understand broadly common sense and then build on top of that central core at runtime. So at runtime, if somebody tells us a definition of a task and then describes it using some examples, we do it so well. And that is what people started calling as in-context learning, popularized by GPT-3 starting from 2020, of course, OpenAI. Right? They basically said that, hey, there's no need to fine tune for specific tasks. Let's basically just define the task and call it zero-shot in-context learning, where I'll not basically give you any examples. Maybe I'll just say, translate English to French, and you take cheese and you come up with the French output, right? Or one shot meaning one shot in context learning, not fine tuning. So I'm not fine tuning. I'm not training the model any longer. I have a well-trained core, right? And on top of that, I'm just telling it at runtime, hey, do this task, and here is an example, right? Or hey, do this task, here are some examples. It learns how to do them it generalizes to new examples. Right? So GPT-3 was great, but then OpenAI actually improved it further. They basically said, and they called it clearly as InstructGPT. Not that GPT-3 did not take instructions, but InstructGPT took more variety of instructions and came up with much more accurate output. Right? So clearly, and again, to build that generic core, GPT-3 was pre-trained on much larger data. So if you look at it, 410 billion tokens from Common Crawl. Common Crawl is just the web, the entire of web. A lot of books data, the entire of Wikipedia, you use that so as to train this common core. And that's GPT-3. But then what InstructGPT model folks did, or other, again, OpenAI, but then what these guys did was to actually start from GPT-3 and then ask it questions which are based on these kinds of tasks. Generative tasks, open question answering tasks, just brainstorming, chit-chatting, rewriting. Now they enlarged to these kinds of tasks. These kinds of tasks were chosen because they capture more or less all logical reasoning capabilities of a human being in terms of processing language. So if you're brainstorming with someone, you use some kind of logical reasoning tricks. If you're chatting with someone, you use some kind of logical reasoning tricks, including, of course, what is the right answer for the question, how to negotiate, how to empathize, how to speak in the same style, and so on and so forth, right? So basically, whatever basic core tasks that form the basis of logical reasoning in English or in text, in any text, right, is what defined these set of prompts or sort of tasks. Now, these prompts were given to humans, and in the first step, tens of thousands of such prompts were given to humans, like explain the moon landing to a 6-year-old. And a human labeler came up with some results. These results, tens of thousands of them, were, of course, used to fine-tune GPT-3 model, which already was super awesome, but you fine-tune in many of those ways, many of those prompts, whatever are the outputs from humans, you fine-tune them. And then you essentially, the second step was basically that, yes, this model has now learned how to respond to such prompts, but then maybe it still can be improved. So the way to improve is as follows. You ask the model, explain the moon landing to a 6-year-old. It gives you 4 different results. You ask a human to rank them, much like a mom would rank the outputs from a kid, right? So if a kid basically does well, the mom appraises. If the kid doesn't do well, the mom penalizes, right? So the labeler also did the same thing. They just ranked the outputs, right? Which was basically used to learn a reward model. So a proxy mom in some ways, right? So which could basically then be used at large scale in step 3. So in step 3, you would take large scale number of such prompts, ask the model to come up with outputs, and have this reward model penalize or appreciate the overall model, thus updating its weights, right? Uh, thus updating its weights. But this proxy mom may not be a good mom. So therefore, what they did was once the model was trained well, they would basically repeat the step. So they would go back, iterate the second step. Of course, this also meant more human labeling, right? So as to create a better proxy mom, right? And or a better proxy, a better reward model, right? But then that, of course, give them gains as we see in the ChatGPT models that we work with today. Now, ChatGPT is a much more revised variant of InstructGPT. So InstructGPT is also a fairly new model, March 2022, and that is when, in fact, all of this GPT-X series has been going on. So OpenAI has been investing more and more to improve on InstructGPT. Any public knowledge? There's no good public knowledge about what is the difference between ChatGPT or InstructGPT. We just know that it is an InstructGPT model. How many layers does it have? What further it has been trained on? Nobody actually knows. There's no nice public release around it. Okay. Now we all use ChatGPT. As we know, ChatGPT works really well and has been tested for all kinds of linguistic tasks one can think of. I showed you the demo in the beginning, right? I'm sure you have used it for several use cases. I think using ChatGPT is a great idea because it sort of takes care of, compared to crowdsourcing, it is a very nice way of generating labeled data, cheaper, faster turnaround, agile, as well as high quality. It can also be used for filtering, bad quality data, so like offensive suggestions and so on. You could, in some use cases, not even train a model. So for example, in a travel use case, we basically just needed some outputs, some labeled examples for 70,000, 80,000 destinations. We said, no need to train a model, just ask ChatGPT to generate those descriptions anyway. Yeah. But we all know ChatGPT also comes at a cost. So these models take a whole bunch of capacity to train. Online inference is therefore out of scope right now, right? And the other things that essentially have gained momentum in the past few months, not years, past few months, is prompt engineering. People have been thinking, hey, it's a great worker, but how do we make this worker work nicely? So you have to tell it in nice ways, right? You have to basically put up the prompt, which is way more clear, unambiguous, much more objective in nature, with examples, sometimes with the labeled examples, right? Sometimes also give it prompts which have examples with reasoning, so that it also generates results with reasoning. And oftentimes when it generates results with reasoning, it comes up with better results, it turns out, right? The interesting part is that this model has been trained in such a generic manner that you can actually control for output length. You can tell it, hey, I don't want more, for example, summarize a 10,000 word document into 100 words or 50 words or 20 words. You can control for the output length nicely. You can control for the output language. You can say, write an essay on Indian Independence Day in Hindi versus in English, right? You could also control it for output style. So generate, act like a chatbot as if you're a nice, you're basically a sports chatbot, for example, right? And therefore talk to a human about sports, or talk to a human as if in the style of Amitabh Bachchan, for example, or talk to a human in the style of Garfield, and so on, right? So overall, this is more or less the end of my talk, right? The outlook is super awesome. Go deep learning, right? I mean, lots to do, huge boosts in productivity. I have used these kinds of models for various purposes, right? I mean, some of my own personal use cases as I feel like, right? And I think imagination is no longer the limit. We can go beyond imagination. Such models are helping us enhance creativity, which basically is the next level, right? However, there is some negative stuff about it as well, which I sometimes feel, fearsome. There are unintentional negatives of these models in terms of hallucinations, biased content, toxic content, right? All of us have read these printouts that our bank guys generate. This page is computer generated and hence does not need to be signed. We surely don't live in that era any longer, right? There's a whole bunch of malicious use cases of these models, fake text, fake images, fake videos, leading to significant privacy and security issues, right? So I think as we have this positive outlook, it is super important to think about ethical use cases until law and policy takes over, right? Yeah, that's that. I'll probably stop here. This is a poem generated by these models with an abstract